These are the notes for chapter 24 in the McGraw-Hill book on nuclear chemistry. So I'm going to start out talking about the different types of nuclear radiation. If you have your printout of your notes in front of you, that'll help out. Start out by, we're going to talk about something that doesn't have a whole lot to do with nuclear chemistry, and that's back in 1890, Heinrich Hertz proved the existence of radio waves. Why am I mentioning this? Well, I think it goes a long ways towards you understanding why we named this, or Marie Curie named this, radioactivity. Kind of like the internet's the big deal now. Back then, radio waves were the big deal. They were invisible, but they could make things happen in another room or somewhere else. When you pushed a button over here, it could make something happen somewhere else. So it was invisible stuff, and it was kind of cool back then. So we move on, and we're going to talk a little bit about Wilhelm Röntgen, whose name has been used for one of the units that we'll see later on in nuclear chemistry. Notice that some minerals were able to emit X-rays. He called them X-rays because they didn't know what they were. And they discovered this because chemists at this time were the guys who did the film developing. And it was, chemical process, and they were probably, well, not the only ones. They could teach other people, but they were the guys that prepared some of the emulsions and the chemicals and stuff for the process of developing the pictures and for making the actual film that was used. They noticed that when they set some of these rocks next to the film plates, that they developed an image of the rock when they shouldn't have been able to. We move on and talk about the French physicist Henri Becquerel, and he was dealing with some minerals that glowed. When you shone light on them, they glowed, and he wondered whether these minerals did the X-ray thing also. So he got interested, and he had a couple of folks, probably the equivalent of graduate assistants now, Marie and Pierre Curie. They took this material called pitchblende and worked with it, and she, of course, coined the term radioactivity when they discovered that they were able to emit rays that caused photographic plates to develop through a protective boundary. All three of them got the 1903 Nobel Peace Prize because of their work with radioactivity. So we're going to talk about the types of particles, three main particles that we will start with. There are a few other particles we'll deal with. Alpha particle, if you forget what alpha is, think of helium, 4/2 He, and it's the helium nucleus, not the electrons that go around it. Beta particle, an electron, 0 or -1 e, and also a gamma particle. The symbols for these, you can see that 4/2 He, and the alpha, which looks like a fish swimming to the left, it's the Greek lowercase a. Beta is 0 over -1 e, and the capital B, beta, Greek letter. And then gamma looks a little bit like a seagull kind of turning as it flies, the way you used to draw seagulls in kindergarten probably. And we usually put a 0, 0 for the top and bottom numbers, the superscript that precedes and the subscript that precedes, because it's got 0 mass and 0 charge. So we'll talk about alpha particle first in decay. Decay is when an isotope, we call them radioisotopes because radioactive, when it loses particles from the nucleus. And these particles fly out at a high rate of speed, thus called radiation. Alpha particle is 4/2 He. So when we talk about a decay problem, you're going to put one item in the left, kind of like decomposition, and then you're going to have two or more things on the right. And in this case, one of those things is 4/2 He. And this really isn't that difficult, because all you have to do is make sure that on the left and the right side of the arrow, the top numbers are balanced, and on the left and the right side of the arrow, the bottom numbers are balanced. So in this case, we've got radium-222, and you look at the chart and see, well, that's at number 88. So you put 222 over 88, an arrow. And then on the other side, you know that it's alpha decay, so we've got 4 over 2HE. And then you say, well, let's see, what added to 4 gives me 222, and that would be 218. And what added to the 2 gives me 88, and that would be 86 for the bottom number. We look up 86, bottom right corner of the main part of the chart, and we see that it's radon. So we've just completed our balanced equation. Now, there are some other particles, some gamma particles, and other particles that are given off. This would be basically what I'd be asking you for if I asked for a balanced equation of alpha decay. If I ask you to show all the particles that you know of that would decay, of course you'd include a gamma 0 over 0 also. Beta decay, same process, different particle. In other words, you're going to, in this case we've got thorium 234. Look up there, you see thorium, bottom left of the bottom part of the chart. It's 90, so 234 over 90. Draw an arrow, and then we have 0 over minus 1e as one of the parts. And then we just need to find out minus 1 plus 91 gives us 90, and 0 plus 234 gives us 234. Just balance it just like we did the last one. Finally, we end up with beta decay, or gamma. Gamma decay occurs. It is the way we balance the energy slate for these equations. And, you know, gamma has no mass and no charge. And really, it's just like when you see an explosion, you see light, you feel a shock wave, you hear sound wave comes through. All of these things are ways that energy is given off, and to represent this, we have to balance. We would have to show that to balance the energy slate. Notice here we've got two different. We've got one alpha and one beta, and they both produce a gamma radiation as a product. For nuclear stability, there's 3 or 4 pages where we're talking about nuclear stability. Talk first about transmutation. And transmutation is the changing of one element into another. This is something that the alchemists dreamed about, and they were going about it the wrong way. They were doing standard chemistry with electrons, trying to change, and they didn't have the wherewithal or the knowledge at that time, the equipment to be able to do it. But you can actually change from one element to another by doing nuclear chemistry. Proton and neutrons are called nucleons. They live in the nucleus. Strong nuclear force. We have weak forces and strong forces around us. The gravity is a weak force. This happens to be a strong force. Strong force is the nuclear force, what holds the pluses together when they want to get away from each other, because like charges repel. In nuclear stability, we're going to look at a graph, and that graph is in your book on page 866, and you'll notice that they have graphed on the y-axis neutrons, on the x-axis protons. And the line that is at a 45-degree angle in most of those graphs would be the 1-to-1 ratio. Notice that as we get to the atomic number of 20, basically, the plot of stable nuclei, which is the blue dots in this diagram we have up on the screen, but it's the one that has the dots that are plotted. Those are the actual stable nuclei that exist. From 1 to 20, they are basically the same 1-to-1 ratio. So, and you can support this by looking at the periodic table. Notice that the most common isotopes would be reflected by the fact that the atomic mass is very similar to that number. Carbon has an atomic mass of 12, and that means that the most common carbon would be 12. Obviously, if the most common one was carbon 13 or carbon 14, that number would be higher. But those are not stable. So they don't exist in a stable form for a long period of time. Carbon 14, after 5,730 years, it degrades and becomes something else. So generally, the carbons that are around are the stable ones. So carbon 12 has an atomic number of 6, atomic mass of 12, 6 protons, 6 neutrons. Nitrogen is 7, has an atomic mass of 14, which means the most common nitrogen is nitrogen 14, and that would be 7 protons and 7 neutrons. Same thing, you get the oxygen, it's 8 and 16, neon is 10 and 20. So as you go through these elements, a 1-to-1 ratio is good as long as you're 20 or under, or maybe 18 or under. It starts to wander about 20. Once you get above atomic number 20, there's more neutrons than protons, and you can see that by the fact that this dotted line starts to wander above, which would be more neutrons than protons, and that's because the neutrons have some function or some ability to help the protons be more stable and stay together. And you can see that we get up to 1.38, up around 10, and then up around lead at 82, we're about 1.5 to 1. So there's actually 1.5 neutrons for every proton once you get up that high. Once you get above 20, though, you can see it starts to wander up above the line. It's not 1-to-1. Now, one exception to this, just to make sure that you put this in your thought process, is hydrogen 1 has a 1-to-0 ratio. It only has 1 proton. It has no neutrons. So keep in mind that because it doesn't need a neutron, it just has 1 proton. Proton's not fighting for space because it's the only thing there. So you'll see that it has a 1-to-0 ratio. So keep in mind, hydrogen 1, it's stable. So if you're asked that on a quiz or a test down the road, you know that that one is stable, even though it doesn't follow the 1-to-1 rule. So here's a review again about the nuclear particles: alpha, beta, gamma. Make sure that you know how to do those in decays. We're going to talk about penetrating power of these types of radiation. Alpha is the largest, and it has the least penetration power. It's hardest for it to go through things because it's larger. Paper, paper's enough to stop that. Beta will go through paper, and it'll go into glass or aluminum, and you have a fairly thin sheet of glass or aluminum, a 1/4 inch or so, it'll stop the most beta radiation. Gamma goes right through that. Gamma can actually penetrate through about 6.5 feet or so of concrete, and if you have more than that, you'll stop it. So those are the penetrating powers in alpha order: alpha, beta, gamma. We're going to talk about nuclear fission and nuclear fusion, and we're looking at these a little out of order of the book, but they are in the chapter, and if you need to refer to that, you just look in the index and look them up. That's the quick way to find where they are. So nuclear fission, this is what we use in our power plants, out in our aircraft carriers and nuclear submarines. They're all now using nuclear fission. It's the splitting of an atom, a larger atom, into 2 smaller ones, and that releases a large amount of energy. Nuclear fusion, on the other hand, something we don't do as well. We can do nuclear fusion, we just don't do it in an efficient way yet to make energy. We use as much as we make, and it's basically the putting together of hydrogens and production of helium. There's several different forms of fusion, but here's a good baseline equation. 4 hydrogens, hydrogen 1s, plus 2 electrons yield 1 helium, 2 neutrinos, and 6 gamma particles. Fusion requires such a high temperature, we're not able to do it well. The tokamak, we actually can do fusion. We kind of surround it with this tremendous magnetic field, very strong magnetic field. We keep the 1,000,000+ degree temperatures kind of capped up in a force field, and we can do it. It's just not real functional yet. Detecting radiation. So when we talk about detecting radiation, there are 3 main ways. The Geiger counter. Geiger counters look like like this. And you may have seen one that was red or yellow. I think most of the ones that are little portable ones are yellow, but they all have this wand that is gas filled, and when you turn it on, okay, it beeps every time radiation strikes the gas and knocks an electron out. We call it ionizing radiation. So you can hear that beeping in the background possibly. And there's a little bit of radioactivity there. Not much, because there are going to be anywhere from a strike to 2 or 3 strikes in every 2 to 3 seconds. About a strike per second is pretty common. And it actually sums them up on the screen, a little digital readout, so it tells you that is it's working and it's measuring radiation. Scintillation counter, another way, kind of the same thing, except it uses a phosphor screen. Every time, kind of like a bug splatting on the windshield, every time the ionizing radiation hits, the electron hits the screen, it counts those bright spots. Film ID badges, kind of like this ID badge, it's filled with, on the inside, film that's protected from light. It might have your name or your ID etched on it, and so that way light will pass through and etch your name and ID on the actual film strip. At the end of the day, you hang this up, put it up. Somebody comes in on the night shift, develops the film, looks at it, and if there are little white dots or little strikes on there, then they know that you've been around some radiation. If there are a whole lot of them, then, of course, every time you go through a door, you swipe this. They'll know by the computer record where you've been, and they'll try to match that with other folks that had the same thing happen. They'll try to track down where the radiation leak is. Those are 3 ways that we detect radiation. So that finishes up that first PowerPoint. There will be one other, and start working on your review. There's some practice problems. Go through that. Stay on track. I know it's getting late in the year, but keep up the good work and keep working hard, and we will see you on the next video.